Alright, let's get started with Lesson 4, Ionic Bonding. Ionic bonds are the first type of bond that we're going to discuss here in Unit 3. So let's start out with a definition of what an ionic bond is. Simply, an ionic bond is an electrostatic attraction between oppositely charged ions. So let's give you a quick example of what this entails. So metal atoms typically are positively charged atoms. So let's say like sodium, for instance, it has a positive charge. Nonmetals, on the other hand, are negatively charged. And so let's say chlorine, for instance, which has a negative charge. Now these two ions, when they are in close proximity to each other, they are going to form a bond between themselves. And we're going to represent that bond by creating a couple of dots here. Now that bond is an electrostatic attraction that is between these oppositely charged ions, the negative and positive, and that creates our ionic bond. So ionic bonds are always formed between a metal atom that's positively charged and a non-metal atom that's negatively charged. And so that's something I would write down. Ionic bonds between metals and non-metal atoms. Alright, so here's our example of sodium and chlorine forming an ionic bond, so that we can kind of get in a little bit more detail here. So first of all, let's highlight a couple of important points here. So how is an ionic bond created? Okay, so first of all, we have to have a metal atom. And those metal atoms are going to transfer their valence electrons to the nonmetal. Alright, so there's literally the valence electrons from the metal atom are literally going to be transferred to the nonmetal atom. Now, the results of the metal is going to form the metal will become positively charged. The nonmetal, on the other hand, it's going to gain the valence electrons so that it can fill its outer shell. And the nonmetal then will become negative charged. And the truth of it is by when the metal gives up its valence electrons, it then results in a full valence shell. And the nonmetal, when it gains the electrons, it is also going to have a full valence shell. So they both have complete octets. Now, once those ions are created and we have full valence shells on both the metal and nonmetal, then the two opposite charged ions, the cation and the anion, are going to attract through that electrostatic attraction, all right, or Coulombic attraction, and that's going to hold the two atoms together in an ionic bond, all right? So that's essentially how all ionic bonds are formed, is from a transfer of electrons from metal to nonmetal, all right? And then the opposite charged ions that result form an electrostatic attraction between each other. All right, so let's take a close look here at our sodium here and our chlorine atoms. All right, so let's write the electron configuration for sodium. This should be already in your notes, but I'm going to write it here. So it's 1s2, 2s2, and 2p6, 3s1. Okay, so the valence shell for sodium is the third energy level, and it has one electron in the valence shell. And so sodium is going to lose one electron to the nonmetal. In this case, it's going to be chlorine. So that electron is going to be transferred directly to the chlorine atom. Now let's look at the chlorine. It has a electron configuration of 1s2, 2s2, 2p6, 3s2, and 3p5. 5, okay? So chlorine, its outer electron shell is also the third energy shell. And right now, chlorine has basically 7 valence electrons. 7 valence electrons. But in order to get a complete full shell, chlorine needs to get 1 more electron. And so when it takes that 1 electron from sodium and picks it up, it is now going to add 1 more electron, giving chlorine a total of 8 valence electrons, and that completes the octet for chlorine. Okay, and that will make chlorine happy because it has a complete full shell once it takes that electron, right? So what about sodium? Well, let's look at sodium. So let's look at their final electron configurations once the transfer has taken place. So for sodium, its new electron configuration is 1s2, 2s2, and 2p6. Now, when sodium loses its 1 valence electron, it loses its entire electron shell. And now, with the sodium ion, we have the sodium now has a new valence shell, which is the second shell. And notice how many valence electrons it now has in its valence shell. It has 6 in the p and 2 in the s to give us a total of 8 valence electrons. So, by losing its valence electrons, sodium completes a full valence shell, and it's all happy. The trade-off, though, is that it does become positive charged. It does become positively charged, or a positive 1 charge. All right? Now let's take a look at chlorine. Chlorine's new electron configuration is 1s2, 2s2, 2p6, 3s2, and 3p6. So, in its valence shell, it has then a total of 8 electrons, 6 from the p orbital and 2 from the s orbital, give itself 8 valence electrons. And so both the chlorine and the sodium have full valence shells, and they're both very happy and content. But just like sodium becomes a positive ion, because chlorine gains that 1 additional electron now, it's going to have a negative ion. And because it's negatively charged and sodium is positively charged, they are going to then have to attract and form a bond between them, and that is that ionic bond that we've been talking about, that electrostatic attraction. All right. Now, the electrostatic attraction would not happen unless they are both oppositely charged ions in order to form that bond. All right. So the bottom line is the reason why ionic bonds are formed is to help metals and nonmetals gain full valence shells. And metals will always lose electrons, their valence electrons to be specific, to gain full valence shells, because once they lose their valence electrons, then they have a new valence shell. And nonmetals will always grab a hold of those electrons to fill up their valence shell. All right? All right, so the idea, why then do metals typically form positive ions? Why are they the ones that lose electrons? Well, we've already discussed this in previous units when we talked about ionization energies. So metals atoms having low ionization energies are able to transfer their valence electrons to nonmetal atoms with very negative electroaffinity values. Well, it'll take a moment to talk about electron affinity in just a minute. But metals, because they typically have low ionization energies, they're much easier to remove their electrons than to actually gain electrons. And so they get rid of them. Whereas nonmetals, they have what are called high electron affinity values. Now, just to give you a brief idea, we'll discuss electron affinity a little bit more later on. But electron affinity basically describes how much an atom wants electrons. And the more that they want electrons, the higher their electron affinity values. Remember, affinity means that it likes, it wants, okay? So nonmetals have very high affinity for electrons. They love them, and they want more of them. Whereas metals, they do not have high electron affinity values, very low electron affinity values. Metals just want to get rid of them, which makes sense since they have low ionization energies and so forth. Okay, so kind of think of electron affinity in that terms. Now, when this transfer of electrons occur, each atom now has a complete octet. It is important to remember that the lower the ionization energy for a metal, the more reactive it is. So make note of that. Now, nonmetals have higher ionization energies, so they don't lose electrons very well, but they do have very negative electron affinity values, which we just talked about. So when they gain electrons, they release energy which is more favorable, and this is something that I should point out. Because nonmetals have high electron affinity values, when they gain electrons, they actually release potential energy in the process. And this makes them more stable and favorable overall. All right? So these are some important ideas here about ionic bonding, so make sure you understand these principles. All right, so we have a couple more examples we'll look at with ionic bonding here. So we have calcium and oxygen. And let's go ahead and write out the electron configuration for calcium. I know that you already have this in your notes already, so you can just kind of follow along. Let's do an abbreviated. So, oops, I don't want to use that. I want to use okay. So, argon, and then the valence is 4s2. Okay, so that's calcium. So notice that calcium has 2 valence electrons, and so it's free to give up those 2 valence electrons in the 4th energy shell, and they're going to transfer those directly over here to oxygen. Now, if you look at oxygen, it has basically helium, and then it has a 2s2 and 2p4, all right? So in order for oxygen to get a full valence shell, it's got to pick up 2 more electrons, because if you look at it, it's got 4 valence electrons in the p orbital, 2p, and 2 electrons in the 2s. So that only gives it 6 valence electrons. So if it picks up 2 more valence electrons, then it's going to give itself a total of 8 valence electrons in its outer shell. All right. So oxygen certainly has a high affinity for 2 valence electrons, and it's gladly to take those from calcium. Whereas calcium wants to get rid of them desperately so that it can lose a valence shell and have a full shell. All right. And so let's look at this. As a result, we can see all of this. For calcium, it's now going to have an electron configuration of neon again. And it will then, it'll have a new electron configuration with neon and then 3s2, because it's going to have a new valence shell, 3p6. All right. So it's lost its 4th energy shell, and it now has a new valence shell, which is the 3rd shell, and it has 8 valence electrons on that shell. All right. The trade-off, though, is that by losing those 2 valence electrons, it's going to form a positive 2 charge, or a positive ion. Okay. Oxygen, its electron configuration now is going to be helium, and then 2s2, and then 2p6. So it didn't lose a valence shell like calcium did, but it did pick up 2 more electrons. So now it also has 8 valence electrons in its valence shell. And so now it's got a full shell and happy. But again, its trade-off is now it's become a -2 charged ion. And so in order for this whole situation to work, calcium and oxygen are then going to have to form a ionic bond between these oppositely charges. So an ionic bond between the positive and the negative charged ions. Okay? And that's kind of how it looks like. By the way, if we were to make a formula or represent a formula for this compound, or ionic bond we should say, we would write calcium, the metal first, and then followed by oxygen second. So, and since there's only 1 calcium to 1 oxygen, the ratio between calcium and oxygen is 1 to 1. All right. We call this calcium oxide. All right. All right. We have one more example that we'll look at. We have magnesium, and so let's draw the electron configuration for magnesium. We'll just do the condensed abbreviation. So we have neon and 3s2. Okay, that's its valence shell is the 3rd electron shell. Has 2 valence electrons. Just like calcium, magnesium wants to get rid of those 2 electrons. Okay, absolutely wants to get rid of those electrons. Now, fluorine. Let's take a look at fluorine. Fluorine has an electron configuration of helium and 2s2 and 2p5. Erase that, make it better 5 here. 2p5. So basically, if you look at this, fluorine has 7 valence electrons in its outer shell. And so fluorine only needs 1 more, so plus 1 electron to get itself to 8 valence electrons to have a complete shell. So that means fluorine is only going to take 1 of the electrons that magnesium has. And so that means in order for magnesium to lose its other electron, it's going to actually have to transfer it to another fluorine. All right? So in this case, we're going to have 1 magnesium involved and 2 fluorine atoms involved. Okay? But in the end, let's see what happens when all said and done. So when magnesium loses those electrons, it's now going to have an electron configuration of helium and 2s2 and 2p6. All right? So it's lost its entire 3rd shell, and it has gained or lost an entire shell, and so therefore now the valence shell for magnesium is the 2nd shell, and it already is full. It has 8 valence electrons. So 8 valence electrons, and magnesium is very content and happy, other than it has a positive 2 charge now. Fluorine, on the other hand, it's going to gain an electron, so it's going to have a new electron configuration of helium and then essentially 2s2, 2p6. And so now that's going to complete fluorine's outer shell with 8 valence electrons. And you're going to see the same thing with the other one. It's going to have a full 8 valence electrons as well. Right? The trade-off is both fluorines are now going to be negatively charged. So you have negative, negative. Oops. Got a negative charge and a negative 1 charge versus the positive 2 charge. Alright? But you can see, though, is that the positive and the negative charges are going to attract to form an ionic bond. And the good news here is that we have an even amount of negative and positive charge, so that in the end, this bonding arrangement is going to create an overall neutral situation, because 2 positives cancel out the negative. If we were to write a formula for this, we would say magnesium, and again we put magnesium first because it's the metal. The metal is always written first, and then we put fluorine next, and we're going to put 2 because there's going to be 2 fluorines to 1 magnesium. And so the formula is MgF2, and it has a 1:2 ratio. Alright? And it's very important that when an ionic bond does form, like in this situation, that the ionic charges do cancel out. In other words, that we have the same number of positive and negative charge. So the overall bond between the ions are neutral overall. And we can see that, we saw that back here with calcium too. With calcium being, oops, go back here. With calcium being a positive 2 and oxygen being a negative 2, those 2 charges canceled out, and so that's why we had a 1:1 ratio of calcium and oxide. Okay. All right. Here's a little cartoon, just for fun. I lost an electron. Are you positive? All right. And here's another cartoon. The name's Bond, ionic bond, taken, not shared. All right. So there's just a couple of funny cartoons. All right, let's move on. All right, now that we know what an ionic bond is and how we create an ionic bond, we need to discuss what an ionic compound is. So essentially, an ionic compound must contain both metal and nonmetal ions, which we've kind of discussed already. These ions form ionic bonds between themselves, making a giant 3D structure called a crystal lattice that maximizes the attractions and minimizes the repulsions between ions, resulting in a low potential energy state. So what we're saying here is that both the metal ions and the nonmetal ions are going to form these ionic bonds. And these ionic bonds are going to create an ionic compound, which is essentially a crystal. Or in other words, we could say an ionic compound is a crystal that results in many different metal and nonmetal ions, all attracted to each other through ionic bonds. All right. Now, the ions that are in an ionic compound, they are at a perfect distance from each other that maximizes all the attractions between the negative and positive ions, but also is far enough away from each other that minimizes the repulsion between the ions, such as from the nucleus of these atoms and so forth. All right. Now, the crystal lattice contains the same number of ions as that's shown in the chemical formula. Kind of like we showed earlier, the chemical formula, the ratio is the number of ions that are found in the ionic compound, or at least that ratio is. So I'll explain that in a little bit more in a minute. So the Coulombic forces are very strong in these solid crystal structures, meaning the ionic bonds in the ionic compound are super strong. Coulomb's law predicts that a larger forces and stronger interactions result when ions have greater charges. So that means like +2, +3, +4. Those are greater charges. They're going to have stronger Coulombic forces or electrostatic attractions. And when ions get closer together, so the closer they are and the more charged they are, the stronger the electrostatic forces are, which you know completely from Coulomb's law. All right, so here is a ionic compound. This is salt or table salt here. Okay, and this is what it would look like if you were to look at table salt. It's a crystal. You can see the crystal pattern. And this right here is a model of that crystal, of creating the salt, basically, essentially this. Now, I should mention here that, and I would like you to write this down, all ionic compounds are indeed salts. So anytime you have an ionic compound, you have a salt. So let's just say all, let's write this, all ionic compounds, compounds are salts. Okay, so make sure you have that in your notes. All right, so this particular salt, though, is called table salt. It's the salt that we commonly use to put it on food and so forth. Okay, well, table salt is made up of a bunch of sodium ions and a bunch of chlorine ions, and those sodium and chlorine ions have a 1-to-1 ratio. So we have 1 sodium to 1 chlorine. And so we write the chemical formula like this, NaCl, all right, which is referred to as being sodium chloride. Now, in this model, the sodium ions are the ones in purple, and the chlorine ions are in green. And so we can see that the sodium ions are attracted to the chlorine ions and vice versa to create strong ionic bonds, which then results in this nice crystal structure that is an ionic compound. All right? And so that's essentially what an ionic compound is. It's just made up of all of these ions that are in a particular ratio, a whole number ratio, and in this case, it's a 1-to-1 ratio between the sodium and chlorine. So in other words, every sodium ion in here has a counter chlorine ion to keep it a 1-to-1 ratio. All right, and here's, I think, even a better model to kind of look at this, the 1-to-1 ratio in this compound for sodium chloride. Again, this is an example of a crystal lattice of sodium chloride. Now, each ion is surrounded by 6 ions with the opposite charge, so that there's equal numbers of sodium and chlorine ions. So you can look at here, here's your negative charge chlorine versus your positive charge sodium. And so you take one that is easy to look at. Let's look at this sodium right here. This sodium is going to be attracted to basically this chlorine, this one, this one, this one, and this one. All right? So that should be 6 chlorine ions. 1, 2, 3, 4, 5, 6. And indeed it is. So that sodium ion is surrounded by 6 other chlorine ions, and they're all attracted to each other to create this crystal lattice structure. All right? Now, not all crystal lattices are squared like this. Depending on what the ionic compound is, depending on the ratio of the ions in that ionic compound, is going to determine the structure of what the crystal looks like. All right, and we can show you some examples in class of different structures of ionic compounds based on the ratio. For instance, if you remember our magnesium chloride or magnesium fluoride example, there's a 2-to-1 ratio in this compound. So that means that we're going to have in our ionic compound of magnesium fluoride, there's going to be always 2 more or double the number of fluorine ions than there will be magnesium ions to create the crystal structure of the ionic compound for magnesium fluoride. All right, so hopefully you kind of get that idea of what we're going to be looking at here with these ionic compounds. All right, so I believe that is it for this particular lecture video. I know it's kind of long, but there's some important concepts here with ionic compounds, so I kind of went slow. Please review your notes on this. If you have any questions, come and see me. Prepare for a quiz, study your notes, rewatch this lecture video if you need to. But that is it for now.